All right, this one should be one of the shorter videos of the semester because it's really just got one very narrowly focused idea and example in it. Okay, that topic is something that is usually known as Hess's law, sometimes expanded to call it Hess's law of constant heat summation, which is just a mouthful. But so takes advantage again of the fact that delta H is a state function, right? So that says if I can conjure up any sequence of reactions that would add up to be the reaction that I'm interested in, if I know the delta H's for all those reactions I combined, I would get delta H for the reaction that I care about. It's really hard to make sense of in words. I'm sorry that I never thought of a better way to explain that or a good way to explain that. It sort of makes more sense as an example, right? The equation we saw at the end of the previous video that said use the heats of formation to find delta H for a reaction, in a way is a special version of this, right? Because it says in that case the reactions that we're imagining adding and subtracting to get the equation we want are all the formation reactions. When we call it Hess's law, we usually just sort of expand the realm of reactions we might use to just include any reaction that we happen to know delta H for. So without further delay, let's just get into an example, and hopefully that'll illustrate this concept better. Well, hopefully if I can make the slides work here. So let's do this too. Let's change that, and let's do this. Okay, so here is the problem I'm going to solve. I'm going to take those first two equations. The top one is what? The top one is the complete combustion of propane, right? That's an easy reaction to carry out. So that would be a relatively simple one to measure, right? If I take propane and burn it in oxygen, that reaction is what will primarily take place, and there's its heat of formation. The second one is the heat of, let's call it oxidation of carbon monoxide, converting CO to CO2. The reaction I'm going to use those two reactions to find delta H for the incomplete combustion of propane, right? The reaction on the bottom looks like a combustion reaction, right? But notice it's got CO on the right-hand side instead of CO2. So that's what we call incomplete combustion. That reaction would be really hard, basically impossible to get it to happen on its own, right? There's no way to mix some propane and some oxygen, put them in a container together and set off a spark or something like that and say, just tell them this time you're only making CO, no CO2, right? Because that won't happen, right? You'll always find CO2 in your product as well. The complete combustion reaction, you can make that one happen by just making sure you have excess oxygen, right? Because then you'll end up with everything converted all the way to CO2. So this is actually an example of one that might really have been found this way to get that heat of incomplete combustion, all right? So let's just do the problem now. So here's how I go about doing these. These two on the top, those are the equations that I know, all right? So I like to just label those. So I'm going to call the top one number 1 and the bottom one number 2, okay? And I'm going to use those labels to describe how I'm going about doing things, all right? So I know reaction 1, and I know delta H number 1, I know reaction number 2, and I know delta H number 2 there. So what I want to do is I want to find a way to add, subtract, multiply things with those equations. I want to make a linear combination of those two equations that adds up to the reaction I'm trying to get, okay? Whatever I do to the reactions to get that to work out, I'm going to do the same thing to the heats of formation, okay? So here's how that looks. I like to start off with something that can only be gotten from one place. So when I look at these equations, I'm going to say that it's not so hard to see that because it's going to work out for everything that way, I guess. I picked an example that will work okay. I guess I'm not going to pick the oxygen until last, right? I'm going to let the oxygen just sort of sort itself out at the end because O2 is in both equations that I know, right? So if I start out by saying, well, I need 7 moles of oxygen, there's going to be a lot of different ways I could do that. Right? But I need 2 moles of propane, and there's only one place to get that, right? Here is propane, but up here in my equation that I know, I have just 1 mole of propane. So what I'm going to do is I'm going to multiply equation number 1 by 2. And I'm going to write down what I get for that, right? I get 2, just multiply all those coefficients by 2. 2 propanes plus 10 oxygens. Product side, I get 6 CO2s. And I get 8 waters. Okay. What else do I need? I need over here, I need 6 moles of CO, carbon monoxide. There's only one place I can get carbon monoxide. It's in equation number 2 here. And again, it comes 1 mole in the equation, right? But the other thing that's different now is I need 6 moles on the right-hand side. And what I have up there is 1 mole on the left-hand side. So what I need to do is I need to multiply that reaction by 6, but I also need to turn it around backwards. Turning it around backwards amounts essentially to multiplying it by -1, right? So I'm going to say I multiply that equation by -6. So the minus sign says what was on the left-hand side comes to the right-hand side. So over here, I get 6 moles of CO2. What was on the left goes to the right, so I get 6 moles of CO. 6 times a half, so I get 3 moles of O2. Now I want to try adding those up, right? I could add them all up and then clean things up. I'm going to clean things up first, I guess. So I'm going to do something like, I don't know, let's be fancy here. We'll get a different color. And I'm going to say, here are 6 moles of CO2 and here are 6 moles of CO2. The ones on the bottom are on the left-hand side. The ones on the right are on the right-hand side. This is just like if you did algebra and you found 6x on both sides, you'd subtract it from both sides. So I'm going to kill those off so they're gone, okay? I also have oxygens on both sides right now, right? I have 3 oxygens on the right and 10 oxygens on the left. So I'm going to subtract 3 oxygens from both sides. That'll kill those off, and it'll turn 10 here into 7, okay? That'll get me my actual resulting equation. So now I have 2 propanes plus 7 O2. On this side, I get 6 moles of CO, and I get 8 moles of water. So I check to make sure that this equation and that equation match, right? And they do. So that says I've succeeded in getting a combination that gets me the right reaction. Now, remember I said whatever I did to the reactions, that's what this little keeping score thing is for over there. That's what I want to do to the delta H's. So delta H for the reaction I'm trying to find is now equal to 2 times delta H number 1, because I had 2 times reaction number 1. And then it's going to be equal to that. I put a plus sign, so oh well, plus -6 times delta H number 2. So that's going to be what? 2 times minus 2219.9 minus 6 times minus 283. And again, realize there's positive and negative signs on the delta H's and on the multipliers for the reactions. And so there's a lot of ways to mess this up. Again, it's really important just to take your time and grind through things correctly. That moment when I realize I'm looking at the notes for the wrong problem, but it is nearby, so not to despair. And so if I sum those, my notes over here claim I get minus 2,741.8 kilojoules. So hopefully that's correct for that value. Okay, so that's a way we can find a heat of reaction, delta H, from some other set of reactions that just happen to involve the same substances, okay? The best way to navigate through those, kind of like I did here, is to always start out by trying to pick out the things that you can only get from one place. Oftentimes there'll be a substance or two. They're often oxygen or CO2 or water, something common that looks like it's in several of the equations. If you wait till the end, those things will usually kind of sort themselves out on their own. Okay, so that is my best advice for how to proceed doing those. 117 lab, the last experiment of the semester, I believe, involves you doing manipulation like this from some actual results obtained in the lab. But that lab, you're not doing that for another couple weeks yet, so that's still a ways off, I'm afraid.